All right, let's dive right in. Today, we're tackling one of the most mind-bending, counterintuitive, and honestly, absolutely essential topics in all of science: quantum mechanics. So buckle up because reality is about to get really, really weird. So, let's just start with a big question. Is anything truly certain? I mean, in our everyday lives, things feel pretty solid, right? Predictable. But what if I told you that deep down, at its very core, the universe is actually built on chance, probability, and just pure uncertainty? You see, there's a huge difference between the world we see and the world at the tiniest scales. Our world, the classical one, is predictable. Things follow rules we can understand. But if you could zoom way, way down, smaller than an atom, you'd enter the quantum world. And down there, it's a whole new ballgame. Everything is about probabilities, things act like waves, and the rulebook we thought we knew gets thrown right out the window. So where do we even start to unpack all this? Well, our investigation begins with a first big clue that completely shattered the old way of thinking. This totally bizarre idea that particles aren't just little points of stuff. And that brings us to something called the de-Broglie hypothesis. Back in 1924, a physicist named de-Broglie came along and said, hey, you know how light can act like both a particle and a wave? Well, what if everything does? He argued that all matter, electrons, atoms, even you and me, has a wave-like nature. An electron isn't just a tiny solid ball, it's also a wave, smeared out in space.
Okay, so that idea, it opens up a huge can of worms, right? If a particle is also a wave, what does that even look like? How can something be a specific, solid point and a spread out wave at the very same time? It's tough to wrap your head around.
Let's really think about that for a second. By definition, a particle is supposed to be in one place, but a wave, by its very nature, is spread out. So if an electron is both, where is it? Like really? This question is right at the heart of the quantum mystery. So quantum mechanics has an answer for this. It's a concept called the wave function. Now, don't worry about the math here. The best way to think about it is as a cloud of probability. The wave function doesn't tell us where the particle is. Instead, it maps out all the places it could be, with some spots in that cloud being more likely than others. And this is the absolute key takeaway. Before we actually look for it, the particle doesn't have one single definite location. It kind of exists in all of its possible locations at once, just like that probability cloud. It's the act of measuring it, of looking, that forces it to pick a spot. Until then, it's just pure potential. But you know, it gets even stranger. This whole probability thing isn't just some quirky feature. It's actually governed by a super strict and unbreakable rule, a fundamental limit on what we can ever know about the universe. And this is it, the famous Heisenberg's uncertainty principle. What it says is that for certain pairs of properties, the most famous pair being a particle's exact position and its momentum, which is basically its motion, there's a hard limit to how precisely you can know both of them at the same time. So how does that actually play out? Well, imagine you have a super powerful microscope, and you manage to perfectly pin down an electron's exact position. The very instant you do that, you sacrifice all knowledge of its momentum. You know exactly where it is, but you have zero idea how fast it's going or which way. Its motion just becomes a total blur. And yeah, it works the other way too. If you measure its momentum with perfect accuracy, you know its exact speed and direction, then its position becomes completely uncertain. That cloud of probability we talked about just spreads out all over the place. It could be almost anywhere. It's a fundamental trade-off. You can't have both. And here's the part that really blows my mind. This isn't because our measuring tools are clumsy or not good enough. It's not a tech problem we can solve with a better device later on. It is a fundamental, baked-in law of how reality works. The universe itself puts a limit on what is knowable. So after all this weirdness, I bet you're asking, okay, so what? Why does any of this matter? Well, it turns out that by embracing these strange rules instead of fighting them, we are on the verge of a massive technological revolution. It really seems like a paradox, doesn't it? I mean, how can you build anything reliable on a foundation of pure chance and uncertainty? The answer, and this is the beautiful part, is that the very things that make the quantum world so weird are also what make it so incredibly powerful. To get this, let's just look at the building block of all our current computers: The bit. In your phone, you've got billions of bits, and they're like tiny light switches. They can be either on or off, a 1 or a 0. Simple. A quantum computer, though, uses a qubit. And because of all these quantum rules, a qubit can be a 0, a 1, or a combination of both at the exact same time. So what does this new kind of bit let us do? Well, first, that ability to be in multiple states at once, that's called superposition. You can think of it like a spinning coin before it lands on heads or tails. Second, qubits can be entangled. This means they can be linked in this really profound way so that the state of one instantly tells you the state of the other, no matter how far apart they are. You put these two things together, and you get a computer that can explore a huge number of possibilities all at once. And the way this power scales is just breathtaking. The processing power of a quantum computer grows exponentially. With a regular computer, adding another bit just adds a little more power. But with a quantum computer, every single qubit you add doubles its potential power. The numbers get astronomically big really, really fast. It opens the door to solving problems that are completely impossible for even our best supercomputers today. And that kind of brings us to our final thought here. For all of human history, we've built tools that work on those simple, predictable, classical rules. But now we're learning to build machines that operate using the fundamental, probabilistic, and mind-bogglingly powerful rules of the universe itself. So the question to leave you with is this. What problems could we solve? What could we achieve when we finally stop just observing the quantum world and actually start computing with it?